we see that there are three major conditions in order to get pitting. One is breaks in the films, or there could be other defects such as lack of homogeneity in the film, then presence of halogen ions, chloride, bromide, iodide, fluoride, and stagnant surface condition. And also we need to have a particular surface condition. For example, if there are some inclusions which is on the surface, or if there are sensitized condition, all the things we have already seen. Now, let us get into the mechanism of pitting. If we see the mechanism of pitting, there are three stages for a pitting to occur. One is initiation of pit, and second is propagation, of pit, and at this condition we have autocatalytic nature, and then third stage is basically the perforation or pitting termination. It's actually can lead to leakage. So, these are the three stages of pitting formation, and let us get into the different processes that are going on during these three stages. If you consider the initiation of pit, actually on a surface you have, let us say you have dissolved oxygen, and that too in sodium chloride solution, and then if the metal is passivating in nature. So, let us consider these three conditions. One is sea water, second is dissolved oxygen presence, third is, let us say it is a passivating metal. This can also happen in case of non-passivating metal, but we generally come across this pitting very often and severely in case of passivating metal. Now, let us say on a surface you have, let us say this is my surface, you have lot of grain boundaries, as well as there are many inclusions. These are some of the inclusions, or it may happen, let us say in case of sensitized stainless steel, there could be development of depleted grain boundary zones, and these are basically depleted grain boundary zone, GBZ. ZBZ means grain boundary zone. So, there we have little higher tendency for dissolution. So, initially dissolution would happen all throughout this. Just a minute, you stop for a while. This. So, that means we have some of the sections on the surface of a particular metal when it is exposed to sea water with dissolved oxygen. Now, there are some places, for example, inclusion zones or grain boundary zones. They are some of the areas where we have higher energy compared to the bulk of the system. So, initially if it is exposed to this solution, there could be cathodic reaction. The cathodic reaction is, of course, we know this would be cathodic reaction, and the anodic reaction would be M going to M2 plus. So, this is my anodic and this is my cathodic. This is my cathodic reaction. So, all throughout the surface these two reactions are happening, and initially the metal is going under uniform attack. But since we have some of the zones which are high energy zones, there could be a momentarily there could be a huge rate of corrosion at some particular section or particular point or particular region. Now, let us say at some moment there is a section where you have extra dissolution. Extra dissolution. So, let us say this is my cross section and this is my if I am seeing through this thickness direction. So, I see that there is a little bit of extra dissolution momentarily, and this is the start of the pitting or the initiation of pitting. That means, and of course, the solution is stagnant in nature. So, pit forms. Now, once we have this pit form, let us look into this part and zoom this part. What happens at this zone? So, we have this zone. So, still we see that metal ion is forming. So, metal ion is forming, and of course, this metal ion would be consumed by this electron what are released by this anodic reaction. They will be consumed by, let us say, these electrons are going. Okay, so, electrons are going from several position to several sites. Okay, so, electrons are coming like this. Here also electrons are going. So, oxygen would come and it forms OH minus ion. So, here also oxygen is coming and it is forming OH minus ion, and this side also the same story. So, these electrons are basically consumed by oxygen, dissolved oxygen, and it goes for this cathodic reaction and it forms OH minus ion. Now, the situation is gradually changing. The situation is changing in such a fashion that you see, since it is dissolved oxygen and since initially all throughout the cathodic reaction is taking place, in this section we have more and more stagnant condition, and this looks like a section similar to pitting, similar to crevice, where we have a very small section where we have a very much stagnancy in the solution. So, since this section is stagnant and the other section still little bit of movement could be possible, but still this overall solution is more or less stagnant, but this section would be much more stagnant compared to the other section. So, since oxygen is taking care of this electron, so in this part gradually we will see that the oxygen depletion will take place. Oxygen depletion is taking place, and since this is stagnant, So, oxygen is gradually coming inside, but since the stagnancy is maintained, so oxygen coming from the bulk of the solution to this section would be less. So, we have less of oxygen in this part, more of oxygen in this part, in this section. So, now we have a peculiar situation, and this situation is related to a sort of concentration cell. Concentration cell. Now, since we have low oxygen here and we have high oxygen here, so the high oxygen part will be cathodic. So, this part will be anodic and this part will be cathodic. Why? Because we know that from this, if you see this reaction we can write it in terms of potential E0, which is standard reduction potential, plus RT 4 electron, that means 4F ln PO2 H2O OH minus whole 4. So, this is my equation. Now, if you have a dissolved oxygen, less dissolved oxygen here, so the PO2 in this case would be less and PO2 in this case would be high. So, that means in this case, let me consider that potential is E2 and in this case the potential is E1. So, the E1 would be higher than E2. So, we have E2 zone and E1 zone. So, since E1 in the reduction potential, that is E1 is higher, or the value of E1 would be larger than this. So, this will act as cathode and this will act as anode, and this part will have anodic zone and this part will have cathodic zone. And now, see that we have differential aeration cell or concentration cell, and the largest section of the surface are cathode, and of course, that larger section are more or less cathodically protected, but the anodic part will have a small area and the large cathodic area. So, the unfavorable area ratio. So, more and more anodic dissolution would take place in this zone. So, if more and more anodic dissolution take place in this zone, so gradually we will see that this section we have higher metal ion concentration. Now, if there is higher metal ion concentration, so it is acting like a electropositive section. So, the system will try to neutralize this situation. So, who will neutralize? Since we have sodium chloride, so the chloride ion will try to come in this zone. So, if chloride ion comes to this section, now there are two reactions that are possible. One is metal ion and it will react with H2O, metal ion would hydrolyze and it will form MOH whole 2 plus H plus. If we make it 2, so then 2H plus, this would be 2 then, just a minute, we have to balance this. How we could balance it? So, OH plus H. So, now if we make it 2, yes. So, this is balanced now. Now, we have 2 H plus ion in this section. So, we see that and this is of course a metal hydroxide which would deposit, and depending on the solubility of this metal hydroxide, until and unless the solubility of the metal hydroxide at the surface temperature is not exceeding metal ion, whatever metal ion that is forming, that will go into metal hydroxide. Once the solubility of metal hydroxide would increase, then the metal ion formation in this section would increase. So, once we have hydrolysis reaction, so 2 H plus ion formation would be there. Similarly, since chlorine ion is coming here, the metal ion can combine with chlorine minus, and then of course, it can hydrolyze again and it can form metal hydroxide and HCl acid, and of course, this is the situation. Now, this can also happen. Now, if this happens, then we see that gradually the hydrogen ion concentration in this part is increasing. So, the first case is the initiation. Momentarily some section is dissolved quickly and it forms a small pit. Once pit forms, stagnancy of the solution as well as oxygen depletion forms a concentration cell, and then you have a differential area factor or unfavorable area ratio. So, this section would be preferentially going into the solution in the form of ions. These ions will combine with hydrolyze in the presence of water, forms H plus ion, and as well as chlorine ion would come here to neutralize all those extra positive charges, and then that metal chloride, the salt what is forming there, that would also hydrolyze and then form acid. And of course, there would be chlorine ion concentration also. So, now once we have increase in hydrogen ion concentration as well as chlorine presence, that chloride presence, they will act adversely to the passivity. Okay. So, what would happen? So, these two things, this hydrogen ion, that means if we increase the hydrogen ion concentration, pH goes down. Let us say initially the pH was 7. So, pH can go to 2 to 3. So, it becomes highly acidic. At the same time, since chloride ion is there, so they will act adversely to the passivity, and there could be break in the passive layer. So, break in the passive layer, and as well as this situation is continuously running. So, the situation become autocatalytic in nature. More and more metal ion comes out, more and more chlorine ion goes in, more chlorine ions go in, there would be hydrolyzation, there will be hydrolysis, and metal ion itself can hydrolyze. So, there will be increase in pH and chlorine ion presence, break in the passive layer. So, the passive layer will always be unstable in this zone, and gradually the thing become more and more aggravating in nature, and dissolution would go in like this at a very, very fast rate. So, this is the stage which is the second stage, propagation of pit, which is autocatalytic in nature. Now, since we have this is the thickness, let us say this is my thickness, gradually this will grow, and finally, there would be through nature of the pit, and the perforation would happen and the material will fail. So, this is the mechanism of pit, and you would see that there is a lot of similarity between pitting and crevice mechanism. So, now we have to think of what could be the preventive mechanism. So, if we see the preventive mechanism, whatever we have thought about the crevice prevention, those will apply here. So, the whatever prevention mechanism we have for crevice, that would active here. So, one is all methods Caves corrosion protection processes or protection ways will also act as protective measures for pitting. Second, this is protection, making the passive layer more strong, more adherent, more stable. So, generally stainless steel, if you consider stainless steel, we add molybdenum. So, if we add molybdenum, the passive layer becomes more stable. So, making more stable. And now you see that if there is no stagnancy, now temporarily there is a small dip and the stagnancy of the solution tries to create this concentration cell. Let us say there is no stagnancy. So, oxygen can easily get in here. Okay. So, the cathodic reaction would also happen here, and then gradually this will become, this small groove would go. So, the small groove will not be present anymore, because the concentration of oxygen is maintained same throughout. There is no concentration cell because of movement in the solution. The stagnancy is one issue. So, somehow the material which will be used for some application, let us say pump application, that case it should be operated for continuously, so that there will not be any stagnancy in the solution. Though avoidance stagnancy, that is what the pump, stainless steel pump, that is to be operated time to time when when the system is under maintenance, in order to avoid this stagnancy case. So, if there is stagnancy, pitting can develop. Then we have different alloys are there where we have increase in pitting resistance. For example, if we consider the increase in pitting resistance, bottom would come 304 stainless steel, then 316, then Hastelloy, then it can have titanium. So, it is basically pit resistance increases as we go up like this. So, depending on the situation or depending on corrosiveness of the solution or the environment, we can choose a particular metals and alloys. So, these are some of the basic protection mechanism, and if we follow this kind of protection mechanism, we can avoid pitting to a great extent. So, this is about pitting. Now, let us get into another form of corrosion, that is called intergranular corrosion. Intergranular corrosion, we will look at it. Before that, I missed a point. Let us say this concentration cell effect is active in case of pitting. Now, we have seen that in case of corrosion, we have different forms, 8 forms, and there are different factors. One of the factors is concentration effect. Now, there we have concentration cell, and we have seen that how the concentration cell is forming. Now, one major atmospheric corrosion is due to this formation of concentration cell. That thing let us just discuss a little bit. See, if we see the rainwater or rain droplet which is falling on metal surface, let us say mild steel, and then we generally see that at the center of the droplet the corrosion is maximum. Okay. So, let us say this is the flat surface of that mild steel, and now we have a droplet, water droplet. I have made it bigger, made it big, just zoomed it. So, now if you see this droplet, of course, this droplet outside we have oxygen and this is in the normal environment. So, in the droplet also we have dissolved oxygen, Now, once we have dissolved oxygen, we have an electrolyte, this rain droplet will act as electrolyte, and of course, the metal dissolution can happen since this is mildly acidic. So, we can consider this reaction to be the cathodic reaction. This reaction we can consider to be the cathodic reaction. So, this cathodic reaction can happen, and since we have electrolyte, so this anodic reaction can happen. This is cathodic, this is anodic. So, now gradually this both the reaction are going on and this rainwater is almost stagnant in nature. So, gradually the oxygen inside the part, inside section or the center part of this droplet. So, if we see from top, you will see that this is my section. So, this part we have depletion in oxygen content. So, if you try to measure what is the oxygen content from the edge of the droplet to the center of the droplet, so we can have a decreasing trend in the dissolved oxygen. So, oxygen, partial pressure of oxygen if you consider, so partial pressure of oxygen would be having a decreasing trend. So, this, though I have drawn it like straight line, it may not be straight line, but it would be having a decreasing trend, and this is the 0 distance. Let us say this is my 0 distance and this is the R. So, this point is R. So, it has the lowest, the center would have the lowest oxygen content once these two reactions are starting, and gradually this oxygen level at the center would go down. But since this part which is in direct contact with the atmosphere, so oxygen can go in and then make out whatever depletion of oxygen is taking place. So, we have higher oxygen content in this section, and in this section we have low oxygen. So, same theory would work here. So, low oxygen, high oxygen. So, this part would act as anode and this part would act as cathode, and this is a narrow section. This narrow section would be cathode and the rest of the section would be anode. This section would be anode and this rest of the section would be cathode, since we have a higher oxygen level. So, now we have a differential aeration cell or concentration cell. Concentration cell is basically with regard to oxygen. So, gradually we will see that dissolution pattern would be like this. So, at the center part we have more and more dissolution compared to the periphery part of the water droplet or the rain droplet on a mild steel. So, this is a classic example of concentration cell development, and that consequence would be the corrosion at the center of the concentration, center of the rain droplet. Let us get into the form which is intergranular corrosion. Let us discuss intergranular corrosion. The intergranular corrosion, the name suggests intergranular. So, that means between the grains or at the interface of the grains, between two grains, there the corrosion is happening. So, that is what this name is, intergranular corrosion. Now, if we see a microstructure, polycrystalline microstructure, we have different grain boundaries, and let us say it is being etched by a chemicals. So, when it is being etched by a chemical, that time the first place where the attack would happen, that is basically the grain boundary zone. Why? Because the grain boundary zone has a higher energy level, and if we consider the energy criteria, so G is nothing but minus NFE. So, more would be G, less would be E. So, I will see that this section would act as anodic zone, and the rest of the section where we do not have the grain boundary, it will act as cathodic zone. So, the attack would happen around this section. Now, let us say I would like to go for a higher, more and more etching. So, that means I would like to over etch the surface. If we over etch the surface, we will see that the etch pits are arriving. Those etch pits are nothing but the dislocation surface interaction, and the dislocation is basically penetrating the surface, and the dislocation core has a higher energy. So, those will be active after grain boundary attack. So, then that part will have a feature which is a dark feature, which is called etch pit. Now, during over etching, though we see the etch pit, but we do not generally see that the grain boundary regions are attacked more and more. So, the grain boundary regions, of course, they will be attacked, but the attack severity of the attack along the grain boundary will not be that active or that exuberant in nature. So, we see that though attack is taking place along the grain boundary region as well as active zones, we do not have much of very severe attack on the grain boundary. But the situation would be different if we somehow make the grain boundary zone very active due to three reasons. One is some element segregation, or enrichment with some element. Second reason could be impurity content, higher impurity level along grain boundary, along the grain boundary, and the third reason would be depletion of alloying elements. So, we see some conditions because of these three effects: enrichment of the grain boundary with some elements, impurity increase in impurity concentration along the grain boundary, or depletion of some alloying elements. These three conditions can lead to make the grain boundary so active, the other part will be almost protected, or very little corrosion would happen on the other section of the material except the grain boundary zone, and the grain boundary attack would be so severe that the material can fail because of this grain boundary attack. Now, this kind of preferential attack along the grain boundary is termed as intergranular corrosion. So, if you would like to see the corrosion grain boundary definition, is basically the preferential attack along the grain boundary due to very active nature of grain boundary. So, this grain boundary and this active nature of the grain boundary could be due to these three effects. Now, let us see some of the examples of these three effects, three main criteria where we have this grain boundary attack, preferential attack. And the preferential attack means the rest of the part of the material will not get attacked much, only the grain boundary part will be attacked. Now, one example for this is in case of brass, when it solidifies, generally zinc goes to the grain boundary section, and there could be increased zinc concentration along the grain boundary. So, zinc segregation or enrichment in brass. This example is zinc enrichment in brass. And second case, generally in case of aluminum alloys, iron can go into solution with a very minor amount. Now, this iron, if it is present in aluminum alloys, this iron is considered as impurity in aluminum. So, that iron can also go to grain boundary regions and make the grain boundary very active. And the third example, and this is the most well known and well discussed example, that is depletion of chromium along the grain boundary in case of stainless steel. And that too 18-8 stainless steel or 18-8 austenitic stainless steel. Now, these are the common examples for all those three situations. We will discuss more about this. Now, when we discuss this, we would come to know that why preferential attack is taking place. So, let us see a particular 18-8 stainless steel . Stainless steel, where 18% is chromium, 8% is nickel. Now, in case of stainless steel, because of the presence of chromium in solute solution, that means the chromium is in the substitutional position in case of stainless steel. So, that content of chromium would be effective in forming a passive layer, which is of chromium oxide nature, and that chromium oxide would give the passivity, and that is what the stainless steel does not get the stain. So, it does not have the rust formation. So, the chromium gives the stainless property to the stainless steel, and generally around 10 to 12% chromium in solution that is needed in order to make the stainless steel to be stainless. Now, if somehow the chromium level goes below around 2 to 3% or below 2%, then the stainless would not be maintained, stainlessness would not be maintained. Let us say I have the grain boundary like this, and in case of stainless steel we see the intergranular corrosion, and let us say when this stainless steel is exposed to some seawater or acid solution, we have grain boundary attack, preferentially grain boundary attack is going on. Now, if you see under microscope, we will see that along the grain boundary regions we have small chromium carbide precipitates. These are all chromium carbide Cr23 C6. These are the chromium carbides which are forming along the grain boundary. Now, if you do composition analysis, we will see that in this section the chromium content is still 18% chromium content, but in this section chromium content can go to less than -2. So, that means in the body part we have still 18% chromium, which is the condition that is required for stainless property, that is 10 to 12%, which is more than, this percentage is more than 10 to 12% chromium. But in this section except that chromium carbide part, the surrounding regions of this chromium carbide part, the chromium content is less than 2%. So, once it goes below 2%, so we do not have the protection which is to be given by the chromium in the form of chromium oxide. So, this section there is a possibility of, and of course, the chromium carbide chromium oxide layer forms on this section. This section also the chromium oxide forms, this section chromium oxide forms, and of course, this contains lot of chromium. So, this around this it is not a problem. So, in this will also act as cathodic, because since the chromium, this carbide phase is cathodic in nature compared to iron. But since we have a depletion of chromium, that means it has gone from 18 to 2% or less than 2%, this depletion will lead to form a anodic zone in the depleted part. So, this section would act as anode, the rest of the section would act as cathode, and the chromium carbide also will act as cathode. So, the depleted part will be anode, and the surrounding regions cathode. surrounding region would act as cathode. Now, you see that this anodic part is basically a very narrow region, and the carbides are forming along the grain boundary regions, and the depletion is taking place along the grain boundary regions. So, this is a very narrow section compared to the surrounding cathodic zones. So, you have unfavorable area factor. So, if we have unfavorable area factor, so the dissolution along this zone would be very high, because rest of the part is protected or very little corrosion because of this cathodic nature, and this section is anodic. At the same time, this is a depleted, this is basically a small anodic area. So, the corrosion rate along the depleted section would be manifold. So, gradually the depletion, this intergranular corrosion will get into the bulk of the system, and there could be failure. Let us say if this is under tension, so and the groove is forming, there would be groove formation like this. See, if you see the 3-dimensional nature, along this, if you see the groove is going inside the material, and since this is a sharp groove, the material when it is pulled, it will fail, and there could be a possibility of intergranular fracture surface. Intergranular fracture. Now, if you see further this picture, the situation is like this. Let us say I would like to see what is the depleted zone. So, if you see this is my carbide, chromium carbide. This is my chromium carbide, and chromium concentration, if you see from this is my chromium concentration. So, along the carbide there is a huge increase, but as you go away from the carbide, then you have gradually with the lowest amount of carbide, lowest amount of chromium, sorry, it is basically the chromium content in this zone, which is the grain boundary zone. Actually, if I see this part and see along the thickness direction, I can have a situation like this. So, we see that this is the depleted chromium carbide zone, and this part corrosion would take place. And finally, we have corrosion attack along the grain boundary due to this effect and also unfavorable area factor. So, this is the nature of intergranular attack in case of 18H stainless steel, and the situation would happen if we have preferential formation of chromium carbide along the grain boundary zone. Now, when would there be a possibility of chromium carbide formation along this grain boundary in case of 18H stainless steel? So, for that we need to satisfy few situations. One situation is the carbon content, if the carbon content is more than 0.02%, then chromium carbide precipitation can be possible. So, for that we need to see a phase diagram for stainless steel, austenitic stainless steel, and if we see the phase diagram, now this is phase diagram is basically nothing but the temperature, and here it is carbon concentration. Then if we see that, we will see that the phase diagram is like this, and this is my gamma plus carbide, and this section is nothing but this temperature is around 600 degrees Celsius. This is gamma plus alpha plus carbide, and this part is austenite. Now, in case of iron or stainless, in case of 18-8 stainless steel, this is pseudo binary diagram. Pseudo binary diagram means we have other alloying elements, but actually we are not considering other alloying elements. We are only considering temperature and carbon concentration and trying to see what is my different, what are the different phases that can arise during cooling. Now, we are starting with this carbon content is close to around 0.02 or less. This is this carbon level. Now, let us say I started with the carbon content around 0.08%. Now, when I cool it, and this is the solidus line, then if I come to this place, so I will always see that this much carbon is excess. So, this much carbon is basically this much carbon is excess in the material. So, if we allow some time, then this much carbon would try to come out from the lattice and try to form carbide. And since chromium has a very high affinity towards carbide, towards carbon, and also the chromium content is very high in the 18-8 stainless steel, which is around 18%. So, the chromium will react with this excess carbon, will form carbide. And at the same time, these carbide formation, chromium carbide formation is a nucleation and growth phenomena. So, they will try to form along the grain boundary, because the grain boundary will provide heterogeneous nucleation sites for carbide to form. So, if the carbon content is more than 0.02%, the carbide formation tendency is increasing. This is condition number 1. So, the carbon content. Now, the condition number 2 is, so the condition number 1 is carbon content, the condition number 2 is the temperature zone where we have long aging. If at a particular temperature zone we have a long time aging, we can have carbide formation or chromium carbide formation along the grain boundary. We will see this chromium carbide formation due to aging in a greater depth, and we will also see that because of the temperature and time condition, we can also design the protection mechanism from this carbide related depletion and intergranular corrosion of austenitic stainless steel. Thank you.